Section 9.3, last section for the chapter, is linear relationships. Working example number 1, graph from a linear formula. So, what is a formula? That's the first definition we need to look at in order to be able to deal with them. A formula is an equation that shows how one variable is related to another. So for example, P is equal to 2 times L plus 2 times W shows you how the perimeter of a rectangle, that's what P is related to its length, or L, and its width, W. So we've got 3 different variables here. So this looks like an equation, and it is, but it's also a formula because we have variables that have some specific meaning. So here's an example. A car travels at 60 kilometers per hour. Use the formula D equals 60 times T to express this relationship. And in this formula, D is the distance traveled. So the distance is equal to 60 times T, and the distance is in kilometers. And T is the time in hours. So distance equals 60 times T, time. We're going to make a table of values. So if we know that T is 0, we can use this formula and we substitute in 0 everywhere that there's a T in the formula. So then this becomes 0 times 60 equals the distance at time 0. Well, 0 times 60 is just 0. So at the beginning, there's no distance. Now here's another thing to note. Time cannot be negative in this question, so T cannot be a negative integer. So T is always going to be positive, which means then if T is always positive, then D is always positive as well, or 0. So if T is 1, 1 times 60 gives us 60. And in this case, that's kilometers. And these are hours up above. So at 2 hours, 2 times 60 will give us 120 kilometers. And then at 3 hours, 3 times 60 becomes 180 kilometers. So those are the numbers that we'll put into that table. To find D, substitute each value. Okay, so this is just filling in the blanks. So 60 times 0 is 0, 1 times 60, 2 times 60, and then 3 times 60. That's just showing the work for what we did up above. And again, that's kilometers. D has some meaning, and it's a distance in kilometers. So now we've created a table of values. This creates points that we can graph. These become ordered pairs, where T is our X value and D is our Y value. So in this graph here, our X value, T, time, and we're going up to 4 hours in this particular graph, and our Y value is our distance, or kilometers, is our Y-axis. So here we go, and in this case we're going up to 180 kilometers. So we can graph these ordered pairs. So first ordered pair is 0, 0. You would write that as 0, 0 in brackets. So that point is right here at the origin. The next one is 1, 60. So we can graph that. Find 1 and then go up to 60. So that's our second point. The next one is 2, 120. That's our ordered pair. So we find 2 on our graph across the bottom, and then we go up to 120. So there's our third point. And then our last point from this table is 3, 180. So again, find 3 across the bottom and then go up to 180. So you should notice that this is linear. It creates a straight line. And if you take a straight edge, all 4 of those points lie on a straight line. So that's good. The question is, for part C, is it possible to have points between the ones on this graph? Well, let's think about it. You start at nowhere and you're driving along, You could check to see how far you've gone at 1 hour, 2 hours, and 3 hours, but you could also do it at 30 minutes, that's 90 minutes, and 100 and, what would that be? Well, 2.5 hours. You could check it at any point really along this line. And so yes, in reality, you could have points between these ones. Your car doesn't just jump. It doesn't miraculously jump from 0 distance to 60 kilometers. There is some in between. Time does progress, and you don't just vanish and then magically reappear an hour later, 60 kilometers away, and then you don't vanish again and show up magically 120 kilometers from the start, and then vanish again and magically show up 180 kilometers from the start. It is a smooth transition to go from 0 to 30 kilometers all the way up to the 180 kilometers. A car does drive. So yes, it does make sense. So is it possible? The distance at 2.5 hours, well, let's look at it. 2.5 hours is between 2 and 3, which is going to be right here. So we can have a point right there. So that distance is going to be 150 kilometers at 2.5 hours. You can also look backwards the other way. The time at 105 kilometers, well, 105 is right in the middle between 90 and 120. So on this line, you're going to sit about there. And so that's at about 1.5 hours. So that works. You can pick a distance and figure out how long it takes based on the graph, or you can pick a time and figure out how far you've gone, because all of the points will fall on this straight line. So you really need to think about the context of the information you're working with. How far will the car travel in 3.5 hours? Well, let's look at that. 3.5 hours. Now, to do that, it's probably good to draw your straight line. And in this case, you can do that because all of the points on here will work. And I'm just going to keep extending that line beyond, because it can keep going on and on and on, as long as you don't run out of gas. So at 3.5 hours, you're halfway between this vertical line and this vertical line. Well, that's going to hit right here, which is the next block up from here. And we're going by 30s, so this next line here is going to be 210, because each one is jumping by 30. So when it hits there, it's going to be 3.5 hours or 210 kilometers. So you could actually calculate it too, because you have a formula. You can take 3.5 hours, substitute it in for your t. So then 3.5 times 60 gives you that 210 kilometers. So the car will travel 210 kilometers in 3.5 hours. So you can use the formula, or you can use the graph once you've got some established points to figure out information. There's more than one way to attack it. All right, so with that in mind, you've got a show you know. Give it a go.